Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Yury Aglyamov with us today. And I'm sure I didn't do very good on that last name, but
It was enough saying.
How you doing, Yury?
Yeah, doing well. Doing well.
And what's your geolocation? Where are you at, Yury?
Yeah, I'm in Ann Arbor, in Michigan.
Oh,
So
okay. Okay. So summer's in full roll there.
yeah, but not as bad as in the Southwest.
Now let's say Phoenix, for example.
Are you in Phoenix right now?
I'm in Phoenix, yeah. So it is July 19th of 2023 as we record this, and I'm in Phoenix, and Yury is in Ann Arbor, and yeah, we got another warm one today, but it was all good. It was all good. Not quite as humid as in the Midwest, in the upper Midwest there. So all good. And Yury, what's your position and where? I presume you Michigan?
Yeah, you're Michigan. I've recently started my postdoctoral work, and so I defended at Cornell a couple of months ago, and so the work that's in this paper was done at Cornell as a graduate student, and it's in my dissertation.
So it's Dr. Yury these days.
Yes.
Very good. Congratulations. And Yury, what do you like to do for research?
Yeah, so my research is on the atmospheres of giant planets.
Cool.
And in particular, my dissertation work was on modeling lightning with one-dimensional models in the giant planets, and it was done with in connection with Juno.
Very nice, very nice, cool. And that is going to bring us to this very awesome Planetary Science Journal article. It's open access. We're in the open access era, people. You can go get a copy for free. Go grab one. Giant planet lightning in non-ideal gases. And Yury, take us away.
Yeah, so first of all, I'd like to thank my co-authors and the rest of the Juno team. So this is somewhat of a follow-up to earlier work that I had done with the same people on modeling lightning on Jupiter, and this is for expanding the model to the other giant planets and also planets to Jupiter. And so primarily, what this requires is because and specifically in Uranus and Neptune, you're talking about much higher pressures, and so you need to for where the water cloud is, and so you need to include the non-ideal gas effect and the evaporation of precipitation as it happens on those planets. And we'll get into talk about that a bit more later. And basically to model and make predictions about lightning on Saturn, Uranus, and Neptune.
Okay, cool, nice. Okay.
So yeah, because what we have in terms of observations, so we have a lot of observations for Jupiter and Saturn, including both optical and radio observations. For Uranus and Neptune, we don't have, we have detected Voyager 2, which was the only spacecraft that went to those planets, did detect radio waves that are presumed to come from lightning.
Right, okay, okay.
But was not able to see any optical sign. And yeah. And so I'm talking here about water clouds. The presumption is that those are coming from the water clouds. And because Uranus and Neptune are much colder, those water clouds are far deeper down in the atmosphere. And so that's logical base there.
That makes sense. Okay.
Yeah. And so this is, and there's a big difference between Uranus and Neptune, which also wasn't really easy to understand for what Voyager 2 saw. So the goal here is to see basically whether this is those properties are consistent with what you would expect and whether we can explain them. Saturn's detections of lightning with Cassini, which were overall somewhat similar to Jupiter, although less frequent. And as well, because of course Juno, and this is part of the motivation for the earlier work and for initially starting this work on lightning, Juno had the detection of the shallow lightning, which is happening higher up in the atmosphere than the previous larger flashes that Galileo saw. And so, which was happening at 1 to 2 bars pressure, which is 1 to 2 atmospheres of pressure, which is a lot higher. Yeah, I mean, whereas Galileo saw lightning at mostly around 6 bars of pressure, deeper down in the center of the water cloud.
Okay, I'm with you.
Yeah, cool. And of course, because only Voyager 2 has visited Uranus and Neptune, one of the sort of follow-ups is, what can a Uranus orbiter tell us about lightning, and what should we make sure that we can do to figure that out?
Yes, that would be exciting. Very exciting.
When that happens.
Okay, so there's our motivation. We're going to put together a model.
Yes. So this ultimately is so this is the JIP. So yeah, and this is also a point that Uranus is that lightning would be coming from deep within Uranus, and that's one of the few ways we have to look that far down. Yeah.
Cool. Good.
Now, when we talk about, so numerical model. So this is based ultimately on Carol Stoker's 1986 work with a whole lot of other modifications that have been done throughout time, and it's also based. So this is JIP, Giant Planetary Training Plume Model, which is which was initially put together in the 2021 JGR paper, and JGR Plans paper there, which is simulating an updrafting plume. So it's the Giant Planetary and Training Plume electrification model in being a one-dimensional axisymmetric plume that is rising through the atmosphere as it rises. So well, so once it gains buoyancy, it rises. As it does so, it is entraining surrounding material, which dries it out and makes it less buoyant. And so this ends up eventually slowing it down, and it stops before it flies out into space.
Yes.
In the process, as it's rising, it's a moist plume that's surrounded by dry material. This is the key point and the reason why it's buoyant. As a result, as it rises, it has condensation. The lighter particles can be carried along with that plume. As the plume rises, they collide with each other and grow. And the larger particles then, if they grow sufficiently large, they precipitate out and fall and are removed from the plume. However, as you're going up, new particles are condensing and as per the saturation pressure. Okay. And so, as a result, we start with particles. So when particles condense, they are assumed to condense around a 10 micron radius. And then eventually they can grow up to however big they can get, so that their terminal velocity is carried along. I mean, I think the cut here was 50 centimeter radius. But in practice, the plume doesn't quite get that fast. All right. But you can get large hailstones, although they're not really hailstones, because we are not really considering particles that are quite bouncing around that way, because those are relatively few in number. But they're still quite large sometimes in rapid updraft, if that rapid updraft is taking long. And then, after getting together this particle size profile, and this is based on a particle bin scheme, we then calculate electrification. So you have both the particles that are suspended
Mhm.
at a given level and also the particles that are falling down from above.
Right.
And those can be either liquid or solid, so liquid water or ice. And this then those particles are still going to be colliding with each other,
Yes.
and this transfers charge. So
Okay. There we go.
yes,
Yeah.
yeah, and we are using the non-inductive charge transfer model based on the empirical data by Tiff and Saunders, 1989. And
Okay.
so larger particles will tend to acquire a negative charge, smaller particles a positive charge. And because they have different fall rates, velocities, they have different terminal velocities, the larger particles with, I really hope I'm not mixing up the signs. The larger particles with negative charge fall quickly, the smaller particles with positive charge fall slowly.
Okay.
As a result, there's a negative electric field downward, and so there's overall a positive electric field that's formed upwards. And as a result, there is an overall electric field that is generated from this difference in fall speeds and this preferential charge transfer.
I'm with you.
Yeah, we don't have a full understanding of why that charge transfer happens, but it does.
Okay.
And this is believed to be what's the main mechanisms on Earth for
Okay.
generating lightning, and it will also function on Jupiter or other planets.
Cool.
But you need to and so this requires strong convection. I mean, that's why the thunderstorms on Earth are where you have the strongest most convection.
Got it. Cool. Very cool.
So
Okay.
yeah, and then eventually, when the electric field is high enough, you get electrical
breakdown. Right.
Yeah. So and the material and the actual changes that are being made to account for Uranus and Neptune and Saturn, and this is as I'll discuss later, we also are applying this to Jupiter. But
Okay.
the first point is the equation of state for gas. So the ideal gas equation of state is, while it's good enough for atmosphere, for like 30 atmosphere pressures on Saturn, it's not sufficiently good enough for the higher pressures and higher pressures and relatively colder temperatures for Uranus and Neptune, where water is condensing.
Yes, I'll believe that. Yep, 10 to the 10.
Yeah.
Yes.
Yeah. So there's we use a van der Waals equation. Tristan and Gleason, and so and this is equations 1, 2, and 3. So it's giving us the temperature as a function of pressure, and so PVM over R, it would just be the ideal gas equation of state.
Okay, sure.
P is pressure, VM is molar volume, and so here we are adding two correction terms, the pressure and to the volume, and then using those definitions for the correction terms. Okay.
Very good. And yes, of course, it's an EOS. So then we start taking derivatives. Okay.
Yes. Then we start taking derivatives. And yeah, so the other, and so that was one of the changes. And the other big change was evaporation. And so this is aiming to, so on Earth, usually rain hits the ground in most cases, and it's relatively or snow, and it's relatively rare to have virga in desert conditions where the rain evaporates before hitting the ground. Okay. On the giant planets, there is no ground, and so it's all going to evaporate eventually.
Okay. Effective ground. Okay. I'm with you. Yes.
Yes. So we evaporate according to Knudsen's equation here, and we use an evaporation coefficient from Kessler's 1969 because so this equation is based on surprisingly, So basically, suppose that instead of evaporation, we have condensation. Well, how many particles are able to condense onto a falling droplet? What you have here is that you need molecules of vapor that can hit the falling droplet.
Okay.
And this is given through pressure. And so, and this is the combination of particles that are hitting it because they are, because the molecules falling, and so it's colliding with molecules beneath it, plus thermal motion, Brownian motion that just hits it from all around.
Okay.
And both of those are making a contribution.
Cool. Yes. Yes. Okay.
And so here,
Okay.
now the pressure that matters is partial pressure relative to the saturation vapor pressure. So if there's additional supersaturated vapor in the air, then it would hit the droplet at according to those two equations, and then it therefore creates an overall impact rate. And it happens that this works the same way in reverse, wherein if you are subsaturated and then the water is evaporating faster than it's able to get hit by vapor molecules that fill it back up. And so once again, you still have the same Newton's equation.
Yes. Yes. Because that's what's going to generate our lightning. Yes. Okay.
Yeah, and then if it's if it's in practice, it doesn't evaporate as quickly. There's a number of microphysical processes that is parameterizing. Really, you can argue that Newton's equation has been argued it's exact, but only if you account for a ton of other stuff. So we are just using an empirical coefficient here.
Okay.
That leads it to evaporate more slowly than it would have. And so then this means that you have O for the number of molecules that are hitting you. And so there's any given droplet is getting smaller over time according to the number of impacts. And then therefore its radius is shrinking.
Yes. Yes.
Yes. Now, what we are doing, the particles that we have here are in bins, so they're not, individual particles being tracked. So if you go down a bit, we have equations 10 and 11. So
yes. Okay. Okay.
Yeah. So the bin within the bin that's linear. So the particles at the smallest end of the bin are being moved into the smaller bin. And so
right. Okay. Okay.
Yeah. So so you see, so this is n0 plus, so kr minus r0. R in this case is r minimum, and so that's sort of the density of particles at the smallest end of the bin.
Okay.
Per radius, and so that is how quickly particles are being moved into the smaller bin, and so that's why this is the same.
Gotcha. Gotcha. Okay. Makes sense. Okay, now what we got up here? Okay.
Yeah, and equation 12 is stating that at the same time you also have those particles being moved into the smaller bin.
Mass as well.
And if they are too small for the smaller bins, they just completely evaporate. It's assumed. So, however, at the same time, you also within a single bin, you have an addition. You have the other term, so dmdt is given by equation 12 plus equation 15, and this is just because the radius is decreasing, so you have a mass loss per particle that is summed up over the bin, even though those droplets. So this is a situation where, because you have particles within a given bin getting smaller, even if those are not crossing the boundary between the bins, and so that's making the average particle mass in the bin lighter.
Okay.
And then you have particles coming out from below at the bottom end, and then particles coming in from the top end.
Yes. Yes. Good. I'm with you. Cool.
Yeah, and then we have the calculation of the electric field.
Yep.
And this is actually one. So the approximation that this makes, which is actually a surprisingly good approximation, is that the storm lifetime and indeed even the fall of individual droplets is slow relative to lightning generation. Actually, lightning generation does tend to be, for the conditions we're looking at, generally fast relative to the meteorological timescale. We get rapid flashes, and so you have particles.
Okay.
And the thing is, this model. So what we're really looking at is sort of the peak rate. We're looking at a case where you have intensive convection, and so this is not happening everywhere on the planet. And this is something I'll get into lower.
Sure.
But as a result, what you have is that particles are charging with each other. They grow up to a certain point linearly this time, and then the electric field, which is quadratic in time, but below, but to a large extent, it's because of precipitation meeting these suspended particles. And so below the cloud base, you basically don't have any suspended particles, and so you're not getting a lot of charging. But that doesn't mean you're not getting lightning, because you still have charged particles that are falling at differential rates.
Yes. Okay.
Yeah. And so the draws the boundary as a cloud base. Really, it's a bit below the cloud base, because there's still smaller particles don't evaporate instantly, but that's sort of, and so when we get to the figures, there's discontinuity there, but that's
good. Okay.
It's not actually. I'll discuss it really not much the same.
Okay.
So and so what they're actually generating here is a depth distribution of lightning. And so it's because there's sort of naive assumptions that lightning is happening at a given depth, and it's not. It's not, there's one altitude where all the lightning is happening. It's not that way even on Earth. There are multiple pressure levels where you can have within the water cloud lightning. But yeah.
Okay.
And we then consider the argument about electromagnetic levitation. The issue is basically that once the electric field is high enough, it's generating an electrostatic force on particles that slows them down. And so if it's one-dimensional, eventually you get a stable state.
Yes.
And this is certainly true for one-dimensional case. But when you are looking at a sort of 3D model and one with some amount of random noise, it's a situation where basically it doesn't seem like this would be a stable state. And it requires, and so, but this is going to decrease the flash rate once you get a high enough electric field, and so we are incorporating that.
Okay.
By limiting the energy given up as a point.
Okay, so it's a limiting case. Fine. Okay. Gotcha.
Yeah. Okay. Yep. Okay. Yeah, I don't know. Any questions? Everything clear enough? Everything too obvious?
I think you're being very clear. I'm following right along. You're doing great.
Okay. Good. Down.
Down. Okay. Parameters. We do have
Yes.
parameters in this model.
Yep. So there a number of the parameters are based on the Earth case. And so this is by we are assuming, so when particles are colliding in the upwelling plume, they're either going to collide and stick together, which is required for particle growth, or they collide and bounce off each other, which will transfer electric charge, but does not do particle growth. And obviously, if they're colliding and stick together, then they're not transferring any charge. And so you have both of those which are incorporated. Yeah, and so that's either or, it's not both. at any given collisions. And so we set it at 80 for based on terrestrial lightning rates. The best fit is this, with 80% of the time particle growth and 20% lightning generation.
Okay.
Yep. So let's see. So there's a certain amount of freezing point depression due to, there's a plume radius. There's a certain amount of, there's a stratospheric temperature profile. There's a certain amount of freezing point depression, which is due to ammonia, but there's also supercooling as is observed on Earth. But you frequently know that supercooled water droplets on Earth thunderstorms can go down to as much as 40 Kelvin below the freezing point. But usually it's not necessarily as high. So that's sort of when you still have some liquid. And so the best fit for the Earth calibration is 10 to 20 Kelvin. And so you still have substantial sort of supercooled water. And really it's a gradual phase transition, but that doesn't, as we discussed, it doesn't actually change it. Okay, and then breakdown field is proportional to pressure.
Pressure.
Okay.
Okay, good. I'm with you. Awesome. Nice.
So, let's see, maximum pressure level, 30 bars for Saturn, 2000 bars for Uranus and Neptune. Oxygen abundance. So we are looking at lighting in the water-based cloud, which is generally an ammonia solution cloud, perhaps, but it's still mostly water-based. And so oxygen abundance is it's a direct factor here, and it can be used to constrain the oxygen abundance. And so, because oxygen in giant planetary atmospheres is in the form of water. So, so for we use various values of potential oxygen abundance here for Saturn, and then for Uranus and Neptune. And of course, for Uranus and Neptune, it's as much water as this hydrogen. It's
Yes.
So it's water mass fractions of 20 to 80%.
Very good. Okay. Mass fractions. There we go.
Yes. That is.
Okay.
Yeah, it's the next one. 20 to 80%.
Yes, I'm with you. Okay.
Yeah, good. That's roughly what's estimated, although we don't know exactly. And then there is some amount of dissolved ammonia, and so we set various freezing points that to account for freezing point depression due to antifreeze. The finding for Jupiter earlier was that you actually need some amount of dissolved ammonia to account for the lightning observations. And so here we are once again finding that we need the dissolved ammonia for Jupiter, not actually for Saturn, but and then we set a temperature profile. And the electric field where levitation becomes important. Next page.
Next page. Gotcha. Yeah, the B field. Here we go.
And no, not the table yet. Just the electric. This is the electric field where you stop. You get the levitation that slows down electric field growth.
Okay.
And finally, the biggest impact on the flash rate is from how much water there is, because the more water, the more clouds, the more everything that's generating the lightning.
Okay.
There are some sharp effects from the amount of freezing point depression, so how much ammonia there is in the ammonia water solution.
Okay.
Plume radius is largely being set to sort of being constrained by not being roughly the correct size to not escape into space, but also be vigorously conducting.
Okay.
And the reason is because a plume that's too big would be breaking up into smaller plumes.
Yes. Graph.
And yeah, and smaller and a plume that's too small wouldn't get anywhere.
Oh, yeah. Okay. Right.
Okay.
The results.
Yeah, and here, so look at table 1. So we start with Jupiter because while we're still in the ideal gas regime, the evaporation actually does have an effect, a very straightforward but actually a pretty significant effect when we account for evaporation below the water cloud base. As was shown earlier, that you get lightning actually even at pretty low water balances, but that lighting cannot be deep because you're not going to get precipitation that goes very far beneath the cloud base.
Makes sense.
And so the thing that actually serves as a constraint on overall water abundance, overall oxygen abundance relative to solar, that actually ends up being the deepest flashes, so the depths. And so here we see, 3 times solar is the water abundance that was generally associated with MWR and also with, just what we see for other heavy elements. So nitrogen, for instance, is at 3 times solar, roughly.
Okay.
Whereas 0.3 times solar was the Galileo probe.
All right.
Oxygen abundance, which we suspect is lower than the actual than the global abundance. That this had to be a hotspot where there was less oxygen because it doesn't really make sense for oxygen to be so depleted relative to everything else.
Yeah, I'm with you.
And so a major motivation for Juno was solving this question. It's made some strides, but because of the convection being more complicated than expected, it's hard to say. And so one of the things here is that the Galileo observations of lightning, so the Juno observations with the stellar reference unit are at relatively shallow pressures. The radio observations, it's hard to say where they're coming from. But the Galileo observations were at mostly up to around 6 bars and one flash at 8 bars.
Okay.
Up. Scroll up a bit. Table 1 still.
Oops, sorry.
Yeah, just and so this is why it's worth emphasizing this the deepest possible flashes.
I see.
Yeah, because the more water you have, the deeper the water cloud is. And so if you do want this 8 bar flash, you need more than solar water abundance, oxygen abundance. And that you need roughly 2 solar or more. But on the other hand, most of Galileo's flashes were somewhat shallower. Right. And so if you are talking about flashes at sort of 5 or 6 bars, then you can get away with a solar water abundance and maybe push it to 0.3 solar, although it's hard. And you also, so the amount of the lightning that's shallow and which is what the Juno's SRU detected is it's not all of it, but some of it is shallow. If it's subsolar water abundance, the vast majority of it is shallow. If the more water you have, the more of it is deeper down because the water cloud itself is deeper down.
Okay.
Okay, so figure 1.
Figure 1. Let's take a look. Figure 1. Yeah, we have some flash rates.
Yeah, and so actually, yeah, maybe zoom out to so this is 0.3 times solar for the top graph, 1 times solar for the middle graph, 3 times solar for the bottom, and you can see that all of them have some. So black through red out to cyan is increasing ammonia fraction, so colder freezing points.
Okay.
So at the black line is pure water without any supercooling, and it doesn't generate any lighting at all. The cyan is, your tactic water ammonia, 53%.
Okay, good.
Yeah,
I'm with you. Yes.
And so you get more lighting as previous results showed, if you have ammonia dissolved in the water cloud,
Okay.
you get some amount of, you get lighting from the base of the water cloud to relatively shallow layers. And so if you get lighting, and the more, and so the more water you have, the less ammonia you need, although you still need some ammonia.
Yeah. Yes. See this evolution in the curves.
Yeah.
Uh-huh.
Yeah. So you still get the sort of peak within the cloud.
Yeah.
And then you see there's a discontinuity at the cloud base.
About here,
But for
here.
yeah, so there's two so the top part, which isn't which is less of a discontinuity and more of a change in slope. That is the bottom of the convecting region. That is a level of free convection. And so for the bottom graph, it's at about 4.8 bars.
Yeah.
So, and that's above that level at shallower pressures, you have a convecting plume. And then below that level, you don't have a convective plume. And so because of that, it's a relatively flat line, because you are not talking about different, because you're generating lightning from particles that are suspended and are immediately precipitating out. So you're only looking at the precipitating particles. But you are above the cloud base, so the air is saturated in vapor, so they're not evaporating. And so as a result, you have the exact, you have pretty much the same particle size distribution, because they're all falling down from above. So this is the lowermost non-convecting part of the cloud. And then below that, you have the region below the cloud base where it's all evaporating. But what matters in all of those cases is the integral of the flash rate. It's not it's not actually just because at any given point, I mean, this is the all per pressure step. There are small numbers, but then if you add it up through the entire column, and you know, this lighting is happening through a reasonable sort of top vertical extent any given flash, you end up with a graph like this. So,
right, because you got to integrate over pressure here to get that.
Yep.
Right.
Yeah.
Okay, I'm with you. Yep. And that will give you the total flash rate in watts per square meter. Yes.
Yep.
Good.
So that's that is the Jupiter explanation. Okay, Saturn. So that's table 2.
Yes.
And figure 2.
Okay, figure 2. I'll come back to that table in a sec. Okay, Saturn. Here we go.
Yeah, so there's some general observations. So for Saturn, you actually consistently see less slower upwelling velocity than for Jupiter for the same water abundance. But you actually see, and so this is, so top row, okay, so left column is plume velocity, right column is flash rate. So flash rate is the same stuff that we saw for Jupiter.
Right.
And this is just upwelling velocity. And so top, the rows top to bottom, 1.5, 2.5, 4.5, 7.5 oxygen abundance relative to solar. So increasing as we go down.
I'm with you.
Okay, and so maybe, I don't know, maybe zoom in a bit so that we can see 4 of them at a time.
Okay, let's try that.
Yeah. Yes, this should be good. So this Saturn, yeah. So in general, we see somewhat slower upwelling velocities, but we actually still see pretty similar and even higher flash rates. And you don't have as much of a need for ammonia as on Jupiter. And so we see the blue line, which is basically just supercooling. And you see that in the right-hand plots, even for 1.5 solar water, it still isn't zero, the dark blue line.
Yeah.
So it's still not something that's no lighting at all. So on Saturn, unlike on Jupiter, you don't necessarily need this ammonia antifreeze to allow lighting.
Right, a little floppier. Okay.
And because you're, but also, I mean, you may well still have it. You would think that you would have it, but because in what ways, etc. So different as to not generated with Saturn, but still. So for Saturn here, so the other thing is that the flashes are deeper down than on Jupiter because the temperature profile is colder and the clouds are deeper down.
It's muted. Okay.
And
Yes.
the more water you have, the deeper down this flashlight goes. So if you scroll up and down at 1.5 solar, they're top, this is the area around the cloud base, and as you go down, it goes different.
Okay. Uh-huh.
And you also get more flashes.
Yes.
So the overall power increase.
Pick up. Yep. Everything goes up with solar. Okay.
Yeah, and there's a narrow spike here. The narrow spikes are not an issue because they are integrated out. So that's what I was making a point about this integration.
Okay, thanks.
But yeah, they do end up so you do generate substantial lighting power on Saturn, actually somewhat more than comparable and to slightly more than Jupiter for similar water abundance. The thing is, it's interesting. So what we see on Saturn meteorology in general is intermittent convection. You do not see as many storms as on Jupiter at all, and certainly there are strong storms. When we see them, they're quite vigorous, but most of the time we don't really see convection and thunderstorms and lightning at all. Or, there's usually one storm on the planet at any given time on Saturn. Whereas on Jupiter, all over the planet, you have thunderstorms.
Oh, global. Right. Okay. Very nice.
So, but actually, if you look at within the flash, and so all of this is broadly speaking consistent with observations. So, if most of the Saturn lightning that's been detected has been probably somewhere in this sort of 10 bar, 15 bar pressure range.
Okay.
Somewhere around where we expect the peak. So there's a lot of uncertainty about the measure, the depth. There was one shallow flash that was actually in the Union et al. Paper. It was written as probably a gamma ray burst, but because it was so small and relatively low energy at 3 to 6 bars, but actually this is what we see for shallow lightning on Jupiter, relatively speaking. And on Saturn, and so it's very possible that it was an actual lightning flash itself, although it might have also been an artifact. But on Saturn, everything gets shifted down, so both the sort of main regions that's generating high energy flashes is lower down, and the shallow lightning region is also lower down, so it's at 3 to 6 bars rather than sort of at the 1 to 4 bars for Jupiter.
Okay.
And yeah, you can see that it's sort of, there's not a lot above 3 bars. There's just not much happening in terms of lighting at less than 3 bars.
Right. So,
but it is still a broader distribution. And one note, on Jupiter, what we see and what presumably we would see on Saturn as well, shallow flashes are actually more common, but they're much lower in energy.
Yeah, that makes total sense. Good. Okay. So we go onward to
Uranus and Neptune. So
Neptune.
Yeah, so left to right, this is the left column is plume velocity. The middle column is cloud density, basically. It's a condensate mass fraction. And the right column is water vapor mass fraction. So as we go up, we see that at some point we start to get water condensing out, and so the water mass fraction very rapidly drops.
Right.
And at some point further along, we start to get buoyancy forming, and so we get a plume. And the plume carries along some amount of cloud mass visit, and then eventually it slows back down, and then it hits the stratosphere and things don't really converge, but at that point we don't have actually a lot of lightning anyway. So that's this is not because we're taking big pressure steps. It's in this case we really get issues with the stratosphere, but that's not relevant because there's no lightning there from water anyway because those clouds. But
so inaccurate integration, but who cares? Okay.
It's the stratosphere. But so that's the convection properties. And then and they see that those are extremely high velocities, and because those are extremely high water imbalances and massive amounts of energy that you get dumped into there. And so if you go down to figure 4 now for flash rates.
Figure 4. Okay, gonna zoom in a little bit. Got a global.
Yeah, so black is pure water with no supercooling. Cyan is ammonia water eutectic, and it's so far still somewhat broadly similar, although not identical, because all of this is happening when you're talking about mostly liquid anyway. There's not a lot. So it's interesting because they're colder in terms of temperature profile. This actually, but the way that it ends up working out is that because there's a saturation vapor curve. So for temperature is a function of pressure. There's an adiabat that is steep, and there's an adiabat that is shallow and increasing. For temperature is a function of pressure. And then there's a steep saturation vapor pressure curve. And then the point where they intersect is where you get the cloud base.
Yes.
But so then if you move the adiabat to the left to lower temperature, you end up getting condensation at am I say it correctly at the paper at some point, but basically you end up with both higher temperature and higher pressure at the point where the condensation is happening, because so what we see are, if you look at the left side, we're seeing very high values in principle for the energies. Yes, including one where Python went into exponential notation. Scientific notation, but and what this ends up being basically is that because we have this extremely rigorous convection, we can carry along a lot of heavy particles, and this is a fairly large extent up and down of the atmosphere, and so and of the water cloud, because and so we are able to carry, first of all, we are able to carry, ice, snowflakes and raindrops and so on, very high up in the atmosphere compared to where the water is actually condensing, which is significant. Even though there's no vapors there. And then we can generate lightning there as well. But all of this is assuming that there's this very strong convection. And so sort of, if we extrapolate from Jupiter to Saturn and then try and extrapolate further to Uranus, Neptune, or if we just look at the energy balances, you might expect even more intermittent convection on Uranus and Neptune. And probably, this sort of, and probably to some extent that's true. So it's pretty complicated. But basically, we might expect that lightning is extremely intensive, but that the sort of storms we are looking at are even rarer on Uranus and Neptune. And so then we compare to observations. And this is where it becomes complicated, because basically the Uranus and Neptune observations, we don't have optical detection, but we didn't really try optical detection. We weren't really able to get optical detection because we didn't have an orbiter. We do have radio detection. And again, we are talking about fairly rare lightning at any given part of time. For radio detection, those were extremely weak flashes. And so trying to explain it, so either they were weak because they were inherently weak, presumably because they're shallow, and then they're probably not happening in the water cloud at all, and they're happening in some more shallower cloud, which is not necessarily easy to explain. And also, it's not clear why Uranus should be stronger than Neptune. Or they are happening deep down, and so deep down that even the radio waves are being attenuated. Radio waves are not blocked by the atmosphere as much as visual, it's not as opaque. It doesn't get eaten up by the clouds as much, but it's still, there's some amount of attenuation. Of course, the problem is we don't really know exactly how much. And there's some calculations for it, but we really don't know how likely it is that, and it's most current calculations say that it's very unlikely that we will get this sort of absorption from the water vapor itself. However, you also have the clouds themselves, and of course, the clouds are also scattering radio potentially pretty well, and so that might be playing a strong role.
Okay.
And the reason this is an attractive hypothesis is because Uranus is, in terms of its atmosphere, slightly warmer than Neptune. And so potentially that would, and this actually tends to mean that the lightning is shallower in the model results. And so because it's shallower, it would appear stronger because it's not getting attenuated as much.
Okay. For a given bang.
Right. Yeah, for a given,
Right.
And so potentially that might help explain things. It's, really what we need to do is to try and detect optical lightning. If you're getting lightning in the shallower atmosphere, even at, the sort of pressures you might get in the uppermost reaches of the water cloud, if there's a major convective event, we should be able to see it optically. Okay. And if we can't see it optically, then it's clearly happening deeper down.
Yeah, you got an upper limit. Okay, cool.
And then if we can't see it optically, then that tells us where it's happening in and of itself.
Very good. Cool. And there is, I just want to bring people's appendix. This is a very awesome appendix here, which goes through some of the
so and I want to stress that the model itself is available in Nonideal, and this is a more detailed description of the model.
And it has very lovely table 5, so you can actually know what the symbols mean. Thumbs up on that one. Very cool. Very nice. Yury, I want to thank you so much for walking us through your very
thanks for having me.
ESJ article. And you touched on it a little bit, so let me push on it a little bit. So where do you think we go with this over, let's say, the next couple of years? Is there additional observations, perhaps in other wavelengths that can help? Are there improvements to the model, both in 1D or in 3D, that could be done to help, or some of the charge transferring models that are being used? So where do we go with this topic over the next couple of years?
Yeah, so in terms of observations, of course, the Uranus orbiter is still a lot more than a couple of years away. Although whenever that happens, that will be a big advancement. And right now, Juno is making a lot of lightning observations on its own.
Cool.
And so that's the main source of data for the next couple of years. And then probably we'll have enough in the giant lens for a while. Mm-hmm. But in terms of modeling, so the things that I've sort of been doing work on as an extension is looking at non-water clouds. So I've talked about the lightning in the water clouds, which is the best explanation for everything we see on Jupiter. But in principle, when we're talking about the giant planets, they also have some other clouds. I mean, the ammonia clouds higher up in the atmosphere, and then some clouds as well that are deeper down, which are rock clouds. And so looking at lighting and electrification in those is what there's one paper that we have that's in preparation about ammonia and so forth. But more broadly speaking, in terms of lighting a giant planets, so there is room to do a 3D model. The reasons for a 1D model here, they have a fair bit to do just with computational efficiency, but also really just how well do we know the atmosphere as a whole.
Okay, right. Well, lots of reasons to do 1D.
Yeah, but there's ways you can definitely consider, try and do different modeling approaches as well.
Cool, very good. Well, I really I look forward to seeing this topic evolve over the next couple of years. It'll be very exciting. Very nice. So Yury, thank you once again for walking us through your very lovely article.
Okay, thanks again.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.